Our next question is multivariable calculus, and sub A says we should consider the function f of x comma y equals to e raised to the power x squared y minus x, and we've been asked to compute the gradient and the mixed partial derivative of our function f, and also we've been asked to compute the directional derivative of f at the point 2 comma 0, given the directional vector 1 divided by the square root of 2 negative 1 1. So one thing to keep in mind when we are starting is a point is represented as x comma y. So on a Cartesian plane, a point is represented as x comma y. Now we're being asked to first of all calculate the gradient of our function. So the first step, I'll say step 1, is to compute our partial derivative. We compute our partial derivative. And the partial derivative, the formula is given as a partial derivative of our function f with respect to x, and the partial derivative of our function f with respect to y. Again, we notice that here we have xy, and here we have xy. It's always going to follow this rule. Now, this is a formula you need to know. Just understand the formula. You need to know this formula. And in this formula, we've been asked to compute the partial derivative of f of our function with respect to x. So what we're interested in doing right now is to compute our partial derivative of our function with respect to x. And we know that our function f of x is given as e raised to the power x squared y minus x. Please pay attention to this function. Now, to look for the partial derivative of our function f of x with respect to x, then we can simply write this as the partial derivative of f with respect to f, right, which is the same as the partial derivative of our function of e raised to the power x squared y minus x. So we need to really pay attention to this function. Now, if we look critically, this is an exponential function. We know an exponential function is any function of the form f of x equals to e raised to the power g of x, right? Because there is a power and there is an exponent. And this is the same thing here. If we notice, right, we can consider this to be an entire function g of x. So to get the partial derivative, right, to get the partial derivative of this function with respect to x, we know there is a rule, right, which states that the partial derivative of an exponential function, let's say f of x equals to e raised to the power g of x, it will simply be g prime of x e raised to the power g of x, meaning that we look for the derivative of the power and then we multiply it with our exponential function. As easy as that. So you need to understand the rule. Know that that is how we compute the derivative of exponent. So in this case, we want to look for the derivative of this function e raised to the power x squared y minus x, right? This function. So to do that, we are going to consider our g of x to be x squared y minus x. Therefore, the g prime of x will simply be, now this is a product, right? So we are going to use the product rule. And again, the product rule states if you have our function f of x equals to uv, where u and v are two functions, I can represent them as g of x and h of x, right? Then f prime of x will simply be g of x h prime of x plus h of x g prime of x, where f prime, h prime, and g prime are the first derivative of our function. So again, pay attention to the product rule, pay attention to our function, and pay attention to our exponential function and the derivative. These are the different rules we are going to use in order to solve this question, and it's going to follow the same rules all through. So in this case, we have our partial derivative of this function. So this is our partial derivative. Again, in this case, we are going to consider x squared as a constant. We differentiate y with respect to x. Remember, we're dealing with respect to x, so it will be 0, right? Plus y. We consider now y as a constant. Remember, we're applying the product rule here. Now we consider y constant. We're applying the product rule basically here, right? So we consider y constant. We differentiate x squared. We're going to have 2x minus, now we are with this function, we are done with this x squared y, right? So the derivative of minus x will simply be 1. So our g prime of x will simply be 2xy minus 1. So in essence, we could write this as e raised to the power g of x, and this implies that this will be g prime of x e raised to the power g of x, and this will be g prime of x is 2xy minus 1 multiplied by e raised to the power g of x. G of x is x squared y minus x. Now the reason why I'm so detailed is because, right, I'm creating a video and you need to understand the rule. You don't need to do this in your exams. You simply apply the rule once you understand it. But the reason I'm detailing it is for you to understand the steps needed to get to that solution. So if I'm the one solving this, I don't need to go through this in an exam, especially in an exam. So good, we are done with the first part. If you notice, we have computed the partial derivative of our function with respect to x. I think I should use right here. We have computed this, right? Now we want to compute our partial derivative with respect to y. So we want to compute our partial derivative with respect to y. This will simply be our partial derivative with respect to y, our partial derivative with respect to y of our function f, and this is the same as the partial derivative with respect to y of our function is e raised to the power x squared y minus x. Again, we're going to apply the same rule. We want to differentiate our exponential function with respect to y, so we are going to apply this rule here, but in this case we are differentiating with respect to y. Again, our g of x is x squared y minus x. So g prime of x, right, with respect to y, notice, so this is product. We use the product rule as stated above. So this will be x squared. We keep x squared constant. We differentiate y with respect to y, it's 1. Then plus y. Then we differentiate x squared with respect to y is 0 because x is a function in terms of x and not y. Minus differentiate x with respect to y is 0. So our g prime of x with respect to y is x squared, right? Is x squared. Now we are going to substitute that in our function. Remember, this derivative is simply g prime of x e raised to the power x squared y minus x, right? Remember, here is in terms of y and here is in terms of x. You don't need to do all of this, but just for clarity. So g prime of x here will simply be x squared e raised to the power x squared y minus x. So that's it. Once you have this, right, the next thing we need to do is to compute the mixed partial derivative. It was stated in the question. So it says we should compute the gradient, right? What we've done above here is simply computing the gradient. So our gradient, the gradient of our function f with respect to x comma y is simply the derivative of our function with respect to will simply be the gradient, the derivative of our function, right? The partial derivative of x with respect to x comma the partial derivative of x with respect to y. And we already calculated and saw that the first part with respect to x was 2xy minus 1 multiplied by e raised to the power x squared y minus x, comma, then the partial derivative of f with respect to y is what we just calculated, is x squared e raised to the power x squared y minus x. So this is our gradient. So then that is the gradient of our function. Now we want to calculate the mixed derivative, right? So we're interested in calculating the mixed derivative. So the mixed derivative here is the derivative of x of y of x and the derivative of y of x of our function f. We'll consider the first part, the mixed derivative of x with respect to y of our function. We can rewrite this as the derivative with respect to x of our function multiplied by the derivative of f with respect to y, right? And let me just, yes, that's it. We can write the first part, this function, as this, and we call this star. Then we know that the partial derivative of y with respect to x of our function can be written as the partial derivative with respect to y multiplied by our function with respect to x. this will be our double star. You notice that from double star, we notice that from our previous solution, right? We calculated the partial derivative of our function with respect to y to give us, which gave us x squared e raised to power x squared y minus 1. So we notice that from our previous calculation of the gradient, we calculated the partial derivative of x with respect to y, which gave us x squared e raised to power x squared y minus x, and we also calculated the partial derivative of our function with respect to x, which gave us 2x minus y minus 1 e raised to the power, all that e raised to power x squared y minus x. So we need to really pay attention to that. Now once we have these two, right, these two, this is in terms of x and this is in terms of y. Now once you have the two, you simply substitute it in our equation. Substituting it here, we notice that this will be the same as the partial derivative of x. Now we saw that this was x squared e raised to the power x squared y minus x, right? That's it. And here we saw that this was with respect to y of, with respect to x, we saw that the derivative of our function f with respect to x was 2xy minus 1. So that's it. This is all we need to solve this. So I forgot to write the e raised to the power x squared y minus x. So we can consider just this one, we solve it, right? And then at the end we solve the other part of it. Again, so we are dealing with the product, right? We're going to use the product rule, meaning that we consider one function constant, we differentiate the other, plus we consider the other function constant and we differentiate the next. So in this case, this derivative will simply be, we consider x squared constant and then we differentiate our other function with respect to x. So it will be e x squared y minus x, then plus we consider e x squared y minus x constant, we differentiate with respect to x, or x squared. We notice that this derivative, we already calculated it from above, so you don't need to repeat yourself. So you simply copy the same result if you are 100% sure of your solution. So we saw that from above to be x squared y minus x. If you are not sure, just recalculate it, plus e raised to the power x squared y minus x multiplied by 2x. So this will be, we simply we simplify this, will be 2x cubed minus x squared e raised to the power x squared y minus x plus 2x e raised to the power x squared y minus x. So that's it for the first part, the mixed partial derivative. So we're done with this part. So we have to calculate this other part, which is the mixed partial derivative with respect to y. Again, in this case, we have a product here. If we notice, right, we can consider this as product. So we differentiate this with respect to y, and we differentiate this with respect to y as well. Now differentiating this with respect to y, we are going to have 2x constant, differentiating y with respect to y is 1, plus 2y constant, differentiating x with respect to y is 0, minus differentiating a constant with respect to y is simply 0, right? This was a constant, and this was a derivative, and we kept x e raised to the power x squared y minus x constant, right? Now plus, we're going to keep 2xy minus 1 constant. We differentiate e raised to the power x squared y minus x with respect to y, and we saw from above, right, that derivative is simply x squared e raised to the power that function. So as simple as that, you don't need to recalculate. So the derivative is x squared e raised to the power x squared y minus x. Simplifying this, we are going to have 2x e raised to the power x squared y minus x plus 2xy minus 1 x squared e raised to the power x squared y minus x. So we can factor out e raised to the power x squared y minus x, e raised to the power x squared y minus x. We're going to have 2x. So first of all, notice that this is exactly the same as, so this is exactly the same as this, because these are we call them linear functions. So they are smooth functions. So they are equal. So in an exam, you don't need to calculate the two. Once you identify that it's a smooth function, then you simply assume that the derivative, the mixed partial derivative of the other form with respect to either y or x will simply be the same. But to be safe, always make sure to calculate the two of them if you have the time. So we notice that it's actually the same thing, right? We don't need to proceed. So that is the same thing, right? So it is the same thing. We notice that they are the same. So we can end here. That's the solution. Now, the most important thing is actually the method and the approach in which I'm taking to solve this, and not necessarily the solutions themselves, right? So really pay attention to the steps of that I'm using to solve that. Now, the last part of the question is actually to to the last part of the question is to calculate the directional derivative. So the question says, then given the point 2 comma 0, the directional derivative of f in the direction that, right? So to compute the directional derivative, which is step 3, so step 3 is directional derivative. So the formula for the directional derivative is given as the directional derivative of u with respect to x comma y at the point x comma y, right, of our function f is simply the gradient of our function at the point x comma y multiplied by the directional vector. We have been given the directional vector. We have calculated the gradient. What we need to substitute is actually the point 2 comma 0. So what we'll be computing is simply the gradient of our function at the point 2 comma 0 multiplied by our directional vector that we saw above. So in fact, you can stop the video at this point and just simply move on if you really want to see how it's computed, right? So to do that, we're simply going to, first of all, we will go back to our gradient, right? The gradient function that we saw above. We calculated our gradient and we ended up with the gradient here, the gradient to be this function. So we're going to substitute the point 2 comma 0 in our function. Substituting 2 comma 0 here is going to give us 0 minus 1 e raised to the power minus 2 comma, this will be 4 e raised to the power minus 2. So this is so we can further simplify it to be negative e raised to the power minus 2 comma 4 e raised to the power minus 2. So we saw here that our derivative with respect to x, right, with the point 2 comma 0 is minus e raised to the power minus 2 comma 4 e raised to the power minus 2. So those are our two functions. That is the grade. That is our gradient. So that is our gradient at the point 2 comma 0. And we saw that our directional derivative from the question was 1 on 1. Our directional derivative was 1 on root 2 negative 1 1. So in this case, we're simply substituting it. So it should be e negative 2 comma 4 e raised to the power negative 2 multiplied by 1 root 2 negative 1 1, and we can factor this to be the dot product of negative e 4e to the minus 2 dot product negative 1 1, and further simplify that to be 1 root 2. This will give us e raised to the power minus 2 plus 4 e raised to the power minus 2, which will be 5 e raised to the power minus 2, 1 on the square root of 2, and 5 e raised to the power minus 2. So that's our solution. So see you guys in the next video.